Hey guys, welcome back to another video. My name is Dylan, and in this one, we're going to dive into the 5 most commonly misanswered, incorrectly answered, however you want to say it, maths, sats, strands from children in year 6 halfway through the year. Now, all of this data came again, once more from Learning by Questions, and this is just a reminder, in no way are we advertised by Learning by Questions. It's just a system that we love to use, and we use a lot of their blogs and their data analysis, which is just fantastic. So thank you to them for doing all of this work and this research. And I think it's time we just dive straight in. So we're going to work backwards from 5 to 1. So let's take a look at the first strand. Every strand has this weird number and letter combination code. So this one is 5G2B, and it is to distinguish between regular and irregular polygons based on reasoning about equal sides and angles. And you'll see the number here on the right hand side, 41%. That is how many children answered this strand correctly. So it's quite low to start with. It's only going to get lower. Wait and see what number 1 is. But here's an example of a question then, because what I did was I went to previous SATs papers and I typed in this code, and then questions appear. Now, they don't always appear every single year, but I managed to find this one from a recent SATs paper that says match each shape to the correct name. And what we're having to do here is identify not only whether it's a pentagon or a hexagon, so that would be another strand because some questions cover multiple strands, but also you can see we're going to have to discern between irregular and regular shapes. So this is the type of question children they slip up on, because honestly, over the past few years, if you take a look at how much time is dedicated to shape across the year, it's not much. And it may be something that's squeezed out in year 3 and 4 as we try and catch up from previous years and missed learning, etc. But let's take a look at this question then so we can see how to solve it. Firstly, pentagons and hexagons. Well, a pentagon has 5 sides, a hexagon has 6 sides. You just need to know that. And you also need to know the definition of regular and irregular for polygons. So a regular polygon is a shape, a 2D shape with 3 or more straight lines, and it's regular if all of the lines have the same size length and if all of the internal angles in the shape are equal. So if we take a look at this first shape here, this is a hexagon because it has 6 sides, so we know it's either going to be the second one or the third one. But now we need to decide, is it regular or irregular? And this is where children are falling up. So based on what I just said, hopefully you can see how this top one is a regular shape. So it's a regular hexagon because every single side is the same length, and we can see the angles inside where 2 sides meet, they are all equal, and it gives us that regular looking shape. Let's look at this one now. Well, it's 5 sides, so it's a pentagon, but is it regular or irregular? And hopefully you can see this side here is much longer than the top sides, and also this is a right angle here. Oh look, this is a right angle here. Are they all right angles? No. This is an obtuse angle. It's much bigger. So the angles and sides aren't the same, so this is irregular. So it's an irregular pentagon, so it goes to the top. Here we have another pentagon, and each side is the same, each angle is the same. So this is a regular pentagon, which leaves us with a hexagon that's irregular at the bottom. So knowing what the definition of regular and irregular is going to be a big difference maker and something we can focus on for most children in order to make a bigger move. Let's look at the next one. This was 6P2. So you can see they're all very, very random seeming, but they all mean something. Translate simple shapes on the coordinate plane. So on this question here is a shape, and we can see 39.4% we're getting this right. So it is creeping down. There's a big jump in a minute, you'll see. Here is a shape. Draw the shape after it is translated 8 units to the right. So this is a straightforward question, but clearly it might be a time thing in school. We're not getting time to cover these questions properly, but it's something we need to practice and get right every time. So whenever we translate a shape, we pick one of the corners. I'm going to pick this corner here, and we need to go 8 units to the right. So that's going to be 1, 2, 3, 4. This is where it can get tricky because the number puts some children off and they skip over it. So let's count again carefully. 1, 2, 3, 4. The y-axis would count as 5, 6, 7, and then we have 8. I'm going to make it bold to stand out. I'm going to do the same here just to make sure. 1, 2, 3, 4, 5, 6, 7, 8. Cool. So that's 8 across there. Now this one. 1, 2, 3, 4, 5, 6, 7, 8. We can see that goes there. And then finally, finish off with the final corner. 1, 2, 3, 4, 5, 6, 7, 8. That's one way of doing this. I'm going to get my straight line tool. You will be using a ruler and a pencil to do this. very accurately right into the corner where the lines cross over. And there's your answer. That's it. It's as simple as that. And over 60% of children were getting this question wrong. So it is something we can have a quick win for here, I think, with a very clear strategy on how to count across, basically. So match each corner and you'll get it right. It's as simple as that. For some of these strands, I've got a couple of questions. So here's another one for this strand. It is basically the same thing. Here is a shape on a grid. The shape is translated so that point A moves to 7, 8. All that's different this time is it's also testing your knowledge of coordinates. So it's going to sprinkle in some other strands sometimes, but hidden in here still is translating simple shapes. So let's move point A to 7, 8. So we're going to find 7 across and 8 up, which gets us here. So point A has moved across and up. So this is a significantly harder question than the last one, but it still comes under the same strand. So for this one, we need to move across and up. So how far right are we going to go? 1, 2, 3, 4 across. 1, 2, 3 up. So 4 to the right and then 3 up. Now there's a couple of ways we can do this. We could do each of the corners and map it across, or we could just notice that this corner at the top here that I've just coloured, let's call it B, I notice that's 2 across from A. So I'm just going to go 2 across over here because it's going to stay the same distance away. Then I'll notice this line is 1, 2, 3, 4, 5 tall. So I'm going to go 1, 2, 3, 4, 5 down to here. And I'll notice again, look, if I've just mapped this one, I could easily map this corner down the bottom. It's going to be underneath A. And then the last one to map is this corner where we go back inside of the shape. Now this is 1 across and 2 up from the bottom left. 1 across and 2 up. And now we've mapped every corner. So a couple of methods on how we can do that. Once again, I'm going to go to my straight line tool because what you would be doing in these questions is making sure that the lines are straight. Not like that. Look, this is what can happen when I'm using a computer. Lines are straight. You're going to do much better than I am. And then you're going to make the new shape just like that. So that is that strand, okay? Translating a simple shape. You can see how we can build on it and make it trickier as we go through. I have a very quick message now. Top Dog Tutoring, that's who we are. You can see it in the top corner. Hayden and I have created a whole bank of resources, whether you're in year 4, 5 or 6. We have lots of 11 plus prep for the younger children in 4 and 5. Loads of SATs practice if you're in year 6. You can see here, it's just an example of some of the lessons that we've got. For example here, negative numbers, rounding, ordering and comparing. We have hundreds of them. Hundreds. So you can scan that QR code there and it'll take you to our website where you can access this page and see all of the resources. And there are some free ones available to you. Just make an account and you get access to free lessons straight away that you can try out. And it looks like this. We've got some video recordings. So if you love our YouTube videos, wow, you're in for a treat because there are literally hundreds and hundreds and hundreds of lessons in there, 20, 30-minute long. We've done so much recording for this. You're going to get a homework as well, an independent task to complete with every lesson. So a little worksheet that you can answer questions with. And if you're thinking, well, how will I get my questions checked? We've done a homework walkthrough. There'll be a homework walkthrough there on every page too, where we go through the answers to every homework. There's so much. Just give it a scan, guys. Go and try it out. It is completely free, okay? If you just make an account, you will get free access to lessons for year 4, year 5, and year 6. And if you like what you see, well, you know what? You can get access to the rest of it as well. Back to the video. So, next one. This is the third one, and we can see now it's down to 36.4% of children getting this right. This really, really interested me. I'm going to start with this question, because this says convert time from analog to digital 24-hour clocks. There wasn't a lot of this in recent tests. And the first question that came up was this one. Now, as we read it, you might have the same thought that I did. Amina went to a concert one evening. It took her 1 hour and 20 minutes to get there from home. She arrived at 7:10. At what time did she leave home? Are you thinking the same thing as me? Where's the analog clock? Where am I converting it into digital? What's an analog clock has a face and it's got hands and it goes to 1 to 12. What I think is going on here, and I can only guess because this is the official tag that was given to this question. So they clearly think it fits into here somehow. Maybe what they're actually testing here is the fact that we've written a time in words and now we're going to want the time in a digital version. Maybe that's what it is. But let's take a look anyway. She arrived at 7:10. So it might be the fact that just changing 7:10 into this is enough to warrant them giving them this code. I don't know. But what we do know is it took her 1 hour and 20 minutes to get there. So we need to go backwards 1 hour and 20 minutes. So let's jump backwards 1 hour. We get to 6:10. And then we jump back 20 minutes. I'm going to split it in half to 2 10s. 10 minutes back would be 6. Another 10 minutes back would be 5. And we know there are 60 minutes in an hour. So 10 minutes fewer than that is going to be 5:50. So she left home at 5:50. 10 to 6, got there at 10 past 7. That would be 1 hour and 20 minutes. So obviously, after I saw this, I thought, I'm not convinced this is the best example of this type of question. So I did find this one as well, which fits in much better. This clock shows this time twice a day. So this is an analog clock. Tick the 2 digital clocks that show this time. Now we have digital clocks. This is straightforward now conversion. So looking at the top, it's not quite 3 o'clock yet. The hour hand isn't at 3, so it's going to be 2 something. And then how many minutes past 12 have we got? Well, that's 15 for a quarter. That's 30 for a half. Another quarter around 3/4 would be 45. So this clock is showing 2:45, which means we can tick this one straight away. But now again, the extra layer in this question is knowing that a digital clock can reset every 12 hours. Okay, so a digital clock can reset again, and we might then notice it would say 2:45 p.m. But that's not going to help us. We don't have 2:45 a.m. and p.m. We need to be knowing how a 24-hour clock works, which is why this is the perfect question for this strand. Because in a 24-hour clock, the hours just keep totting up. We can get to 12:45, which would be 10 hours later, and then we can get to 13:45, which would technically be 1 o'clock, 1:45, and then for us to get to the next one, which would be 2:45 in the afternoon, it would be 14:45. So we can tick this one. Little shortcut, if you've got the morning time in a 24-hour clock, you just add on 12 hours because that's half a day, and that's when it resets again and goes round. So there is a much better, I think, example of a strand that is converting time. But just beware, this is a very low percentage. We're down to our top 2 now. Let's take a look at number 2. 6G4A. Find unknown angles in any triangle. So this was the second most incorrectly answered strand that we've seen from our data from learning by questions. So 2 of the angles in the triangle are 70 and 40 degrees. You might be thinking what I thought when I saw this. Where's the triangle? Well, it's all in words. Jack says the triangle is equilateral. Explain why Jack is not correct. There's a few ways we could go about this. We could literally try and draw the triangle. This is not going to be to scale, okay? Let's say this is 70. Let's say this is 40. You could try and work out this one as well. That's fine. You'd actually get 70. It would not be an equilateral triangle. And that's the question. So you couldn't just do this. You could draw it, but I'm going to need an explanation. And the explanation is going to be something along the lines of, let me just get my my font ready here. Let's drag this up. And I'm going to say something along the lines of, let's do it over here. The triangle does not have equal sized angles, so it is not equilateral. Okay, so that's my explanation. It's gone behind me. I'm going to move it up. The triangle does not have equal sized angles, so it is not an equilateral triangle. It is as simple as that. I'm going to bring this to the front so it can fit nicely into my explanation box. The drawing backs this up, and what we need to know here is the definition of equilateral. An equilateral triangle is a regular triangle, like we talked about from earlier. It has equal size length and equal angles in the middle. It would have 60, 60, and 60. So any explanation as to understanding this would get you the mark. Finding unknown angles, we kind of don't need to find this unknown angle, but this is still tagged as this type of question. The reason we don't really need to find this type of angle is because if we're told one angle is 70, one angle is 40, that's enough information to prove Jack wrong, because an equilateral triangle has 60, 60, and 60. So yeah, another strange tag, but I'll tell you what, guys, it's not as strange as this tag. This question was also tagged. Let me just set this up for you. This was also tagged as find unknown angles in any triangle. Okay. Guys, I don't know. I've only been a teacher for over 10 years and I love doing maths. I'm a maths specialist. I do loads of videos on maths for you guys. I'm not sure that's a triangle. What do you think? Let me know in the comments down below. Is that a triangle? No. It's a quadrilateral. It's got 4 sides. I have no idea why this was tagged. Find unknown angles in any triangle. And also, this one here, I can't even really demonstrate this one to you properly because it requires using an angle measurer, using a protractor. So you would have to line up your protractor. What I will do is show you this, that in a protractor, we have a big protractor, looks like this, like a semicircle. That's a very rough drawing. And you'll see in here, there's some lines that we can match up, and there'll be a line going up like that. Now, what's really important is this dot, we match it exactly to the edge here. So it looks like this, and then we can read off what the angle would be. So if you imagine a protractor on top, it would look like this, and then you'd read off the angle, okay? We have done a whole video on using protractors and rulers from last year. Go and take a look at it. It's still very useful now if you want some help on using a protractor. But I just wanted to point out to you how this certainly is a very strange tag. I don't know why they have tagged this question as find unknown angles in any triangle. This is not a triangle, okay? Let's just be clear about that. We're going to number 1 now. Look at this drop off. We started off at like 41%. We're down to 36%. You might think, oh, okay, so the most commonly mistaken strand, it'll probably be like, I don't know, like 35% or something like that. No. Only 21.4% of children in year 6 get this strand right. Solve problems involving division. Now, I've got a few theories as to why. My first theory, division is hard. Okay, that's a straightforward theory. My second theory, it very often is built into a wider problem with lots of steps. And this is what I found when I looked for questions with this strand. Look at this 2-mark question here. The manager of a flower shop orders 4 boxes of red roses. There are 50 roses in each box. The manager makes bunches with 6 roses in each bunch. What is the greatest number of bunches that can be made? This is such a long-winded question. Now let's see. Where's the division coming in? Because straight away I see 4 boxes with 50 in each box. That's multiplication. So 4 times 50, that's going to get us to 200. Okay, so there are 200 roses. And he makes roses with 6 in each bunch. This is where the division comes in. But this is why it's such a tricky question, Strand, because it's embedded in problems. And this problem uses any remainders, and we have to try and, what's the word, I suppose, understand what the remainder actually shows. So let's do 200 divided by 6 because we have bunches of 6. 6 is into 2, obviously don't go. 6 is into 20, 6, 12, 18. So 3 is as close as I can get with 2 left over. And I've got 20 again, so I know this is 3. Remainder 2. So the question says, what is the greatest number of bunches that can be made? Well, we can make 33 bunches, okay? The remainder 2 sometimes confuses people and they just add it on. No. Let me show you exactly what these numbers represent here. 200 is how many roses we have. 6 are how many in a bunch. And then that means at the top, that's how many bunches we make. We can make 33 bunches of 6. We can prove this by doing 33 multiplied by 6. We get 18, then we get 18 again. 198 roses have been used. So the 2 is the leftovers. There were 2 single roses. Look at my awful roses here. That is so bad. But you know, they're roses, okay, I promise. There were 2 left over, so they can't be made into a bunch. So when the question says, what is the greatest number of bunches that can be made? It's 33. Because the 2 cannot make a bunch of 6. So this is why I think this is one of the trickiest strands, because it's also so often embedded in a much wider, trickier problem. Guys, I hope you found this useful. Remember to like this video, subscribe to the channel. We've got way more videos on the way, and share it with as many people as you think will find it helpful. I'll see you again next time for another video. Bye, guys.